Here we have a problem on evaluating limits. That is limit extends to infinity x to the power 1 over x. Okay, let me take the given limit as it is. That is limit extends to infinity x to the power 1 over x. Okay, now when what I'm going to do is I'm going to directly substitute the given limit for x. That is, I'm going to substitute this infinity for x. When I do so, infinity to the power 1 over infinity. So here in the given function, so wherever I find x, I just plug in infinity for it. So infinity. So whenever I divide a non-zero number by infinity, so it will result 0. So I'm getting infinity to the power 0. So actually it is called indeterminate form. Let me write it over here, indeterminate form. So whenever we get indeterminate form as a result of in evaluating limits, so what we will do is we'll be using L'Hopital's rule in the given function. But before we use L'Hopital's rule, we have to use logarithm in evaluating this limit, because in the given function, we have the variable x at the exponent. So when you evaluate a limit for a particular function, and if you have variable at the exponent, and also when you directly substitute the given limit and you get indeterminate form like infinity to the power 0, so what you need to do is first you have to use logarithm in the given function. So for that, in the first step, what I need to do is I have to take let y equals to x to the power 1 over x. So this is a given function, or the stuff we have over here has to be equated to y. Now we have a function defined by y in terms of x. Now what I need to do is I have to take a natural logarithm on both sides. When I take natural logarithm on both sides, I'm getting ln y on the left side and ln x to the power 1 over x at the right side. Okay, here, so the reason why we take natural logarithm is when I take natural logarithm, so I can get rid of the variable at the exponent using the properties of logarithm. So that is, if I use the power rule of logarithm, so the exponent we have at the argument over here can be moved in front of the logarithm, and it has to be multiplied by the logarithm. So whenever the argument is an exponential term, I mean argument of a logarithm is an exponential term, so the exponent we have at the argument can be moved in front of the logarithm, and it has to be multiplied by the logarithm. This is the power rule of logarithm. So to get up the variable at the exponent, we use logarithm. I mean, we take natural logarithm on both sides. So and also particularly, why do we take natural logarithm? Why can't we take some other logarithm? Because if I take natural logarithm, and I may get a situation to use L'Hopital's rule. L'Hopital's rule means I may have to find derivative. So if I have natural logarithm in derivative, easily I can get derivative, because, for example, let's consider a natural logarithm of x. If I want to get derivative of this natural logarithm of x, is just 1 over x. Easily I can get the derivative of a natural logarithm. So that's the reason I'm taking natural logarithm. So okay, now let's use power rule on the right side, power rule of logarithm on the right side. That is the exponent over here can be moved in front of the logarithm. Then I'm getting 1 over x times ln x. Okay, now so what I can do is ln y equals to 1 over x times ln x can be written as 1 times ln x is ln x over x. Okay, now what I need to do is I have to take the given limit on both sides. That is limit extends to infinity ln y equals to limit extends to infinity ln x over x. Okay, now let's substitute the limit infinity for x into this function over here. When I do so, ln infinity over infinity. Okay, so natural logarithm infinity is still infinity, and already we have infinity in denominator. Again, this is called indeterminate form. So simply I'm writing as IDF. So again, I'm getting an indeterminate form. So when now, even after having taken logarithm, I'm getting indeterminate form as a result. So now I can use L'Hopital's rule. So where I should use L'Hopital's rule? I have to apply L'Hopital's rule in the step which comes right before where I applied the limit. So this is a step I have applied the given limit infinity for x. So just consider the previous step over here. So in this step, particularly on the right side, we have to apply the L'Hopital's rule. We are not supposed to do anything with the stuff on the left side. So this stuff should be written as it is, and we have to use L'Hopital's rule. So when I use L'Hopital's rule, what should I do? So in this function, I have to find the derivative of the numerator and denominator separately. So usually when I find derivative of a function which contains variable in both numerator and denominator, we use quotient rule. But when I use L'Hopital's rule, I'm not supposed to use quotient rule. I have to find the derivative of the numerator and denominator separately. Then I have to plug in the given limit for x, and at that time I have to keep the stuff on the left side as it is. Okay, let me continue this on the next page. Okay, this is a step we had on the previous page before we applied the limit. Okay, now I'm going to use L'Hopital's rule in this step. So by L'Hopital's rule, So when I use L'Hopital's rule, I should not touch the stuff on the left side. So what I need to do is I have to write the stuff on the left side as it is, that is limit extends to infinity ln(y). So only in the stuff on the right side, I have to use L'Hopital's rule. That means I have to find the derivative of this numerator and denominator separately. So limit extends to infinity. When I find the derivative of this ln x, already we know that the derivative of ln x is just 1 over x, and the derivative of this x is just 1. Okay, limit extends to infinity. So whenever I divide any stuff by 1, so I'll be getting the same stuff. So when I divide 1 over x by 1, I'm still getting 1 over x. Okay, that's all the simplification we can do. So now I can apply the limit over here. So that is 1 over, we can apply the given limit for x, that is infinity for x, 1 over infinity. So here I divide a non-zero number by infinity. So whenever I divide a non-zero number by infinity, that is when I divide 1 by a very large value infinity, so it will result 0. So now I got the result of this stuff, that is limit extends to infinity ln y equals to 0. Okay, whenever I take a limit for a natural logarithm, so the natural logarithm alone can be moved out of the limit, that is natural logarithm of limit extends to infinity y equals to 0. So what is the base of this natural logarithm? So we know that the base of a natural logarithm is e. So if I actually here we have a logarithmic equation, if I convert this logarithmic equation to exponential form, what should I do? So I have to move this logarithm to the other side of the equation. When I move this natural logarithm to the other side of the equation, I have to consider only the base of the logarithm on the other side. So the base of a natural logarithm is e. So when I move this natural logarithm to the other side, so I have to consider only the base of this natural logarithm, that is e. So the stuff which already exists on the other side will become the exponent of this base. On the left side, we have limit extends to infinity y. Okay, limit extends to infinity. And according to the stuff we have on the previous page over here, we know that y equals to x to the power 1 over x. So the y, whenever we get y, it can be replaced by x to the power 1 over x. So here we have y. So this y can be replaced by x to the power 1 over x. And the value of e to the 0th power is 1, because for any finite value, if we get 0 as exponent, its value is just 1. So I just evaluated the given limit. So the given limit is equal to 1.